Okay, hi, welcome to another pre-recorded lecture. And today I'm going to start by finishing the partitions subject with the following nice result. So remember, a partition is a sequence lambda of is a weakly decreasing sequence of positive integers. And the curious claim, which I'm going to prove today, is that the number of partitions of n into, right, so that's partition of a number as opposed to of a set. Number of partitions of n into odd parts. So odd parts means each part has to be odd. Not that the number of parts has to be odd, but each individual part has to be odd. So this number equals the number of partitions of n into distinct. Yeah, so let me write odd parts and distinct parts. Just to give you an example of what I mean by that is maybe, okay, which number should it? Maybe 7. So let's say n is equal to 7. Then odd parts, 7 is, well, it's either equal to 7, or that's an odd part, or 5 plus 1 plus 1, or maybe 3 plus 3 plus 1, or 3 plus 1 plus 1 plus 1 plus 1 plus, yeah, that's it. Or also 1 plus etc. plus 1, right? That's 1, 2, 3, 4, 5 ways. And so there's odd parts, but for the distinct parts, I can say that 7 is, well, also 7, or 6 plus 1, or 5 plus 2, or 4 plus 3. Right, that's, the parts have to be distinct, but that's the only restriction. And what else? I think that there's only 4 plus 2 plus 1. That's, yeah, so I think that's it, hopefully. So the claim is that there's 5 ways to partition into distinct parts, and there's also 5 ways to partition into odd parts. And that's always, the number of ways is always the same. So how do you prove such a result? And that's actually one of the cases where using Young diagrams is not helpful. Well, there are some proofs using Young diagrams, some bijective proofs, but yeah, what we're going to do is a bijective proof, bijective proof, but it's not going to deal with Young diagrams at all. So yeah, you can pause the video and try to think about what the proof should be. It's tricky. So the idea, the main observation, which you probably know from high school, is that any positive integer can be uniquely factored as a product of an odd integer times a power of 2. I mean, that's a very simple observation. And yeah, so the way we're going to use it is we're going to start with a partition into odd parts, maybe something like this. 3 plus 1 plus whatever, and then I'm going to convert it into, I'm going to use this observation here in the following way. So let's say let lambda be a partition of n into odd parts, and for each j, let me assume that so there is the corresponding odd number appears r sub j times in lambda. So that's like the multiplicity of 2j plus 1 in lambda. So maybe like 1 appears 4 times in this partition here. So r sub j would be equal to 4. Yeah, and then what I'm going to do is I'm going to construct a partition into distinct parts using these data. So the goal is to define a partition mu into distinct parts as follows. So the idea is so I'm going to represent every part of mu in this form. So I'm going to specify the j and the k, and then that would specify this integer uniquely. So the idea is that mu contains this integer to j plus 1 times 2 to the k, if and only if. And now I look what I do is I have j and k. So how do I determine whether mu contains this part or it does not contain? Well, I look at the binary expansion of r sub j. R sub j, you can write it uniquely as a sum of a bunch of powers of 2. Right? That's the binary expansion. If and only if 2 to the k appears in the binary expansion of r sub j. So that's it. That's basically the end of the proof. So claim, which the proof of which is an exercise for you, is that this gives the desired bijection. Which, yeah, so why would it be a bijection? Well, conversely, if you give me a partition mu, right, it has distinct parts. So I can look at each part, and I can factor it uniquely in this way. And then I just say that then 2j plus 1 is going to be a part of lambda, right? And its multiplicity is going to contain it's going to be 2 to the k plus, well, there could be several parts of mu with the same j but with different k's. So I just sum these 2 to the k's together to get r sub j. Its binary expansion is going to consist of different 2 to the k's. And yeah, so let me try to give you, and also you can see that if you give me for different j's and k's, all these integers are going to be different. So that's it. It is true that the image of our bijection gives me only distinct partitions. Anyways, here's an example of how this proof works. And actually, I have recorded it here because this way I'm not good at summing up a lot of integers in my head. So let's say I have lambda. So remember, lambda is a partition into odd parts. So 9, 9, 9, 9, 9, 5 times, and then 5, 5, 5, 5, 5, 5, 12 times, and then 3, 3, 1, 1, 1. So it's a partition of 114. Yeah, I wanted a big example because for small examples, this bijection is not that clear what it's doing. So, okay. So I can write lambda in the following way. I can say that it's like 5 times 9 plus 12 times 5 plus 2 times 3 plus 3 times 1. I'm just recording these numbers in this form. Yeah, and now what I'm going to do is so these numbers here are r sub j's, right? So I'm going to replace them. I'm going to look at binary expansions of r sub, right? So I need to look at binary expansions of r sub j's. And yeah, okay, so I just need to represent every number as a sum of powers of 2. 5 is 4 plus 1. 1 is a power of 2, right? And then 12 is 8 plus 4. And 2 is just 2. And 3 is 2 plus 1 times 1. And then, basically, I mean, this description is kind of involved, but what you actually do is, once you have used the binary expansion, now you just open the brackets. So just expand the sum. So 4 times 9 is 36. 1 times 9 is 9, plus 40, plus 20, plus 6, plus 2, plus 1. And that's the result is your partition mu into distinct parts. So mu is, you just have to sort the answer. 40, 36, 20, 9, 6, 2, 1. Mu has distinct parts. And to go back, you would have to if I just show you mu and don't show lambda, then you would have to factor a power of 2 out of each of these integers, and then you kind of reverse this whole procedure. Right, you factor a power of 2 out of each integer, and then you group them according to whatever the odd number you get times a power of 2. So that's the proof, which, I mean, I think it's a curious fact. I was gonna give it as a homework, but I decided that it's better to explain it in class because it's instructive. It's a tricky bijection which is not using Young diagrams. So sometimes you can just manipulate the numbers in a clever way. Anyways, that's all I'm gonna say on partitions. Most of the work on partitions you're gonna do in your homework. And for the rest of this lecture, what I want to do is I want to give a summary. Because next week we're going to start talking about generating functions. And so today I'm just going to, so far we've been just counting different families of objects. And so what I want to explain today is a story which is, it's called the 12-fold way. The 12-fold way. Which, yeah, this expression is due to Giancarlo Rota, who happens to be my grand advisor. So he's the advisor of my advisor. Yeah, the 12-fold way. And what is, I mean, that's a poetic name, but what are we gonna do? And the idea is we're gonna count the number of ways to put a bunch of balls into a bunch of boxes. So yeah, suppose we want to put, so we have n distinguishable, yeah, I'm just gonna abbreviate distinguishable by dist, and distinguishable balls and k distinguishable boxes. So the balls are labeled and the boxes are labeled, and then you're going to ask 3 questions. Eventually I'm going to ask 12 different questions, but for now let's stick with 3. The first one is how many ways different ways to put the balls into the boxes. And so that's question number 1, and question number 2 is going to be same as question number 1, but with an extra condition, so that no 2 balls occupy the same box. And the third one is going to be the same as the first one, except that so that each box contains at least 1 ball. At least 1 ball. So that's the classical formulation in terms of words, but of course what I'm going to need is a formulation in terms of what we are used to in this class is formulating this in terms of bijections and injections. Yeah, maybe should I? Yeah, let me try to give an example. Before I formulate in terms of surjections, let me just, to make sure it's clear what I'm talking about. So here are some examples. The examples are, well, you have distinguishable boxes. So the boxes are labeled A, B, C, D. Boxes are labeled. And also the balls are labeled. So maybe you put ball number 1 into box A, ball number 2 into box D, ball number 3 and 4 into C, 5 into D. So that's an example of an object appearing in question number 1. Just arbitrary ways to put distinguishable balls into distinguishable boxes. And well, I mean, of course, you can do the same. I mean, you can no 2 balls occupy. Yeah, anyways, that's the. If you put at least 1 ball in each box, or you put at most 1 ball in each box, you get examples for the second and the third questions. But now I guess. So the question I'm going to ask is how to state these questions in terms of bijection, injection, and surjection. Surjections. And I'm assuming by now it is very easy for you to reformulate things like that in terms of, I mean, the hardest part is to not confuse which ones are which. And so one is just you count arbitrary maps. So 1 is you put just with no restrictions, you put n balls into k boxes. So you count maps f from bracket n to bracket k. And for 2, right, you have no 2 balls occupy the same box. So right, this map assigns, there's n balls, and to each ball you assign a box, which is labeled. And so in particular, if no 2 balls occupy the same box, that means that any 2 elements of bracket n have to be sent to different elements of bracket k. So that is injections. two counts, you count injections. F, yeah, between the same pair of sets. And for 3, you count surjections. Right? Each box must contain a ball, so that means that F has to be a surjection. So yeah, so far it's very easy, but now what I'm going to do next is I'm going to introduce, well, I'm going to say that maybe the balls are indistinguishable, or the boxes, or the balls and the boxes. So there's, so far this is 3 questions, but then there's many more. Similar questions when either the balls are indistinguishable or the boxes are indistinguishable, or both the balls and the boxes are indistinguishable. So the total is 12 questions. Right? For each of the 4 possibilities of distinguishable and indistinguishable, you get to ask 3 questions. So now let me try to give you more examples of what do I mean by distinguishable and indistinguishable, although it's probably very clear. So the first example is where everything is distinguishable. Now for the second example, yeah, so here boxes are labeled and balls are, yeah, let me write distinguishable. Distinguishable, distinguishable. Now, what if the balls are indistinguishable? Well, yeah, you draw something like this, you still label the boxes. So the balls are now indistinguishable, and the boxes are still distinguishable. So you count pictures which look like this. And similarly, you can, if you just erase the labels of boxes, so you consider boxes to be indistinguishable, boxes are indistinguishable, then you just so you can kind of you can permute the boxes, and then the result would not change. And finally, you can even consider the case where the balls and the boxes are indistinguishable and the boxes are also indistinguishable. So naturally there is a different number of each of these pictures, and then if you put restrictions, then you also get many more different pictures. And yeah, so the goal of this lecture is to fill out this table. Right, you have on the left you have distinguishable or indistinguishable options for the balls and the boxes, and on top you have either you take arbitrary maps, or you take injective maps, or you take surjective maps. And yeah, so I suggest that you just pause the video and then you try to fill out all these places. It's what is very neat about this 12-fold way is that it includes all of the objects we have studied previously. So in particular, yeah, all the partitions and serial numbers and whatever will appear in here. And so if you can fill out the whole table without peeking into the lecture notes, then you can just stop watching the lecture. So you can fill out this table and then check with the lecture notes if everything is correct. Then you don't have to watch the video. But I'm just going to go through each of these cells in the table and fill out the answer one by one. Yeah. So okay, let us start. I'm gonna, well, first of all, actually, let me try to, since I'm gonna care about these maps, let me try to rigorously say what I mean by boxes being distinguishable or indistinguishable. I mean, that's kind of intuitively clear, but still I would like to, I mean, in this class I would like to be mathematically precise as much as I can. So what does it mean that the balls are indistinguishable? That means that I'm going to consider these maps f from bracket n to bracket k modulo an equivalence relation, which the relation being that I'm allowed to relabel the balls. And what it means is that the two maps f and g are equivalent if and only if there exists a permutation h from bracket n to bracket n such that f is equal to g composition with h. So that's the mathematical notation for, right, so what is composition? This is equivalent to saying that for each I in bracket n, f of I is equal to g of h of I. And then I say that f and g are equivalent. So it's easy to check that this actually defines an equivalence relation. It's reflexive and transitive, symmetric. And yeah, so that's, and that this permutation h literally just permutes, it relabels the numbers, right? It relabels the numbers on the balls. So once you kind of forget the labeling by allowing all possible permutations of the numbers of the balls. And similarly, you can say that the boxes are indistinguishable. You consider a similar equivalence relation, right? So f and g are two maps from bracket n to bracket k as before, and then they are equivalent if and only if there exists. So the only difference is that you consider a permutation not of bracket n but of bracket k, such that, and then you take composition on the other side, f is equal to h circle g. Yeah, so that's just the mathematical meaning of rigorous and of mathematical meaning of indistinguishable. It's just an equivalence relation. Okay, so now let me start filling out the table. So the first row is going to be particularly easy and something we have already seen before. So first of all, what about if the boxes and the balls are distinguishable, then there is no equivalence relation. So I'm just looking at all possible maps. So all maps f from bracket n to bracket k. And we already know that the number of those is what? It is, yeah, so maybe I should write down balls and boxes distinguishable. So that's the first row of the table. Okay, so the first row is the number of just arbitrary maps. It's k to the n, as in the previous lectures. The second row, well, then if you ask for f to be injective, so if f has to be injective, then you choose the image of 1 in k ways, and then the image of 2 in k minus 1 ways, k times k minus 1, etc., k minus n plus 1. So that's the following factorial. And finally, if you want to count surjections, well, that one's hard, but we already did that in like a couple of lectures ago. And the answer was, using the inclusion-exclusion principle, we computed the formula, but the answer is basically given by k factorial times s n comma k, the Stirling number of the second kind. K factorial s of n comma k. Right. So these s and k, they count partitions, set partitions of bracket n into k blocks, which are non-empty and disjoint. So, and then you allow, for s and k, you forget the order, but for if you want to count surjections, then you don't forget the order. So yeah, that's the first row of my table. And then let me try to do the second row, which is presumably slightly harder. So yeah, for the second row, balls are indistinguishable, boxes are distinguishable. So that just means that I'm basically choosing, well, I just want to assign a number to each k. So that's sort of like compositions or multisets. Right, you have your boxes labeled A, B, C, and D, and then you just want to put some number of, yeah, so maybe A stands for apple, B is banana, C is whatever, cantaloupe. Then you just put some number of boxes in each. So that's almost literally compositions. Right? Or in other words, you pick some number of apples, some number of oranges or bananas in this case. Yeah, and so for arbitrary f, right, but here I'm considering maps modular equivalence relation. So I get multisets over bracket k. Multiset over bracket k means I'm choosing out of k possible boxes, but I can choose as many in each as I like. So a multisets over k of size n, and we already have the formula. So the answer is n plus k minus 1. Choose n, which is the same as the number of weak compositions of bracket n, well, of n into k parts. So that's the answer. N plus k minus 1, choose n. So now, okay, what happens if I want the condition that f is injective, so there's at most one ball inside each box. That's n balls total, and there's at most one inside each box. So that's just subsets. Injective f means you just take subsets. You take n element subsets of a k element set. So it's a little weird. You get k, choose n as your answer. So yeah, there's that is the easiest, probably the easiest entry in the table. And finally, if you want f to be surjective, then okay, so there is at least one ball in each box. But other than that, you can put arbitrary number of balls on top of that one ball. So the idea is you can remove one ball from each. That's similarly to what we did with weak compositions versus just compositions. From each box, and you get composition, well, basically you get, instead of having n plus k, instead of having n here, you will get n minus k, right? Because after you remove one ball, you get n minus k balls. You put them into k boxes in any way you like. So the answer is n minus 1, choose n minus k. What I did was I replaced n by n minus k in this formula. So that is also the number of compositions of n into k parts. So you see, this is really a summary lecture. You go through all these objects almost in the same order as we did in class. N minus k, n minus 1, choose n minus k is the answer. So far, so good. Let me copy the table again. Now, okay, now what I want to do is I want to consider the third row. So the balls are going to be distinguishable and the boxes are going to be indistinguishable. And right, so my boxes are unlabeled, but the balls, I only care which pairs of balls lie in the same box and which lie in different boxes, sort of. The boxes, I am allowed to permute the boxes. So, yeah, okay. So, if you look at this information, right, each box gives me a set. It gives me a subset of bracket n. And these subsets are disjoint, and together their union is the whole bracket n. So if they all were non-empty, then it would have been literally the Stirling number. But some boxes are allowed to have no balls. So in case of arbitrary f, right, you count set partitions of bracket n into at most k parts. So the answer is a sum of Stirling numbers. S of n comma 0 plus S of n comma 1 plus etc. plus S of n comma k. That's what you get when you put distinguishable balls into indistinguishable boxes. So now what about injective f? Injective f. You're allowed to put at most one ball into each box, and the boxes are indistinguishable. So that case is kind of stupid, right? If the number of balls is higher than the number of boxes, then you can't really do that. Otherwise, it doesn't really matter. 1, 2, 3, 4. I mean, it doesn't matter which box you choose because they're all the same, and you put at most one ball in each. So the answer is basically, it's either 1 if n is less than or equal to k, and 0 otherwise. And finally, for surjective f, what you do is you must put at least one ball in each box. So you get exactly k non-empty blocks, which are disjoint. So this is just the Stirling number. Yeah, so that's row 3. Finally, let me consider the case where the balls and the boxes are indistinguishable, which is sort of the easiest and simultaneously the hardest as far as the counting goes. So first of all, arbitrary. Yeah, first of all, let me draw the picture. You have indistinguishable boxes, and then you have indistinguishable balls. So you can permute the boxes so that the order is weakly decreasing of how many balls in each box you have. And if you want to consider arbitrary f, then okay, so what happens is you get partitions of n into at most k parts. So we denoted this number by we denoted if the number of parts would be exactly k, then that would have been p of n comma k. But similarly to Stirling numbers, we get p of n0 plus p of n1 plus etc. plus p of n comma k, where p, so here p of n comma k is the number of partitions lambda of n such that their length is exactly k. That's a reminder from last lecture. So yeah, you get partitions here, and then if f is injective f, then you what you need to do is the entry is going to be the same as here. Right? You want to, if you put at most one ball in each box, then you can either do it in one way if you don't care about the order of the boxes, or 0 ways depending on whether, let me 1 if n is less than or equal to k, and 0 otherwise. And finally, so this is same as above. Finally, surjective f, you have to put at least one ball into each box. So what you get is precisely partitions into exactly k parts. P of n comma k. P of n comma k. So you see, it's beautiful. Like, to go from the third to the fourth row, you just replace s and k by p and k in all these formulas. That's the connection between Stirling numbers and partitions in the most kind of obvious way. So yeah, the point is that you should be able to do this when I wake you up at night, and in all the midterms and stuff. You should be kind of fluent with these things. So if you are having trouble, then you should kind of practice. There's in the book there's practice problems with solutions, which you can study. Just kind of go through all. There's a lot of problems with you have to divide kids into a bunch of groups in some sort of ways. So just go through as many of them as you need to make sure you can just right away say, like, count the number of ways to place balls into boxes with all these different restrictions. So yeah, that's it. Next lecture, I'm gonna introduce generating functions, which are totally different. That's kind of the next level of how you can count things, much more sophisticated than what we did so far. So that's it. Have a good weekend, everybody. I will see you all on Wednesday. And thank you very much.